My name is Jim McIntosh. Jim McIntosh Petroleum Engineering is my consulting company. I've been a consultant in the province for 20 years now and working for various companies for 10 years before that. I've been doing work with Bedrock Energy Corp on the compressed air energy storage at Bayfield, which is what this talk is about.
My name is Sangiuliano. I'm a part owner and the Director of Project Management for Bedrock Energy Corp.
Today we're talking about compressed air energy storage in Reservoir Rock, and in specific, the Bayfield pool, which Bedrock Energy Corp is proposing to develop as a compressed air energy container.
Bedrock Energy Corp is an Ontario company whose vision is to develop utility-scale compressed air energy storage in Ontario and abroad. Currently, Bedrock is focused on converting its Bayfield and Stanley porous rock reservoir assets located in Huron County, Ontario, into CAES facilities in the 1 gigawatt range. CAES is a method of storing electricity whereby electrical energy is purchased at off-peak times to power a compressor to store kinetic potential energy. This kinetic energy is then utilized to power a generator whereby the compressed air becomes heated by the combustion of natural gas on the output cycle, is run through a turbine and converted back to electrical energy and put back on the grid on peak times.
The talk will focus on what is compressed air energy storage, specifically the Bayfield Stanley pools, the reservoir model that Bedrock created and used for the nitrogen sweep and for the design of the compressed air facilities, and finalize with some fine tuning and the next steps. This is a picture of a conventional natural gas turbine. This turbine consists of primarily three areas: an air compression area, which is yellowed in this picture, the natural gas combustion area in the center, and then you can see what's called the power blades, which is where all the energy is created. In the case of a compressed air energy storage facility, all the air compression portion of the turbine is decoupled from the rest of the turbine. In a conventional natural gas turbine, in the range of 40 to 50% of the energy of the natural gas combustion is used to compress the air to stuff into the turbine. In compressed air energy storage, because the air is already compressed and stored someplace off-site, all that power requirement for the turbine itself is saved. So 100% of the energy and heat associated with the air going through the turbine is used to generate power or run the motor, whatever the compressor is doing.
Currently, all operating CAES facilities use underground salt caverns. Notable utility scale ones will be located in Germany and also in Alabama. So Bedrock's Bayfield and Stanley compressed air facilities will be the first utility scale and the first overall to be done so in porous rock reservoir.
Just run over the quick advantages and disadvantages of compressed air energy storage in reservoir rock compared to in salt caverns. Because especially the Guelph age pinnacle reefs in southwestern Ontario have proven to be ideal natural gas storage containers. They can be delta pressured, which means they're pressured to significantly above their original discovery pressure. You can also put higher temperature air down there. You don't have the problems with the salt becoming molten and moving like you do if you put high pressure air down a salt cavern. You can also have large temperature swings without degrading the quality of the reservoir, which you may not be able to do with a salt cavern. The disadvantages are, in most cases, because you're using an existing natural gas pool as your compressed air energy storage container, you've got to get rid of the natural gas out of the pool to start with. So there's work that's done in that. And because your permeability isn't nearly as big as an open hole like a salt cavern is, you need significantly more injection withdrawal wells to be able to handle a pool. This picture shows the general area between Grand Bend and Goderich in Huron County. You can see right there, that's the Bayfield pool. And this pool down here, from the M&R's point of view, they call it the Stanley 4, 7 of 11 pool. We just call it the Stanley pool. Those are the two pools that we're considering to develop.
Ontario is a perfect jurisdiction to implement utility-scale energy storage, given the intermittency of our considerable renewable generation fleet, which is often curtailed or exported at a loss to the States, in conjunction with the commissioning and refurbishments taking place with the Bruce Power nuclear facilities, and also the political push for electrification, such as seen with EVs. Experts predict a 3 to 5 gigawatt supply gap by mid-decade. Bedrock's Bayfield and Stanley facilities can act as solutions to address this supply gap. Both Bayfield and Stanley pools were approved in 2012 to be converted to natural gas storage facilities. And in doing so, that helped characterize the facilities and the reservoirs quite a bit. Unfortunately, at the time, a long, large diameter pipeline was acquired from Lobo to Bayfield, which made that project uneconomic. So in 2017, Bedrock sought out these reservoirs and developed a plan to convert them to compressed air energy storage. The pools are at advantageous location given that they're close to the Seaforth transmission station. There is a 500 kV line not far from the sites, and also they're close to the Bruce facilities and a number of large-scale wind generation sites.
As Stephen mentioned, both pools were approved by the Ontario Energy Board for natural gas storage, but have never been converted. The next few slides will go through the geological data that was used as part of the Bayfield pool approval. In front of you here is the 3D survey that was shot over the Bayfield pool. The Bayfield pool currently consists of two individual wells. There's the Porter well up in the northwest and the Granger well kind of in the center of the pool. The Granger well was partially cored by the operator when it was drilled back in the 1950s, so it provided significant extra data for us. Based on this 3D survey, we went to an engineering outfit called Computer Modeling Group, CMG, out of Calgary, to create a detailed reservoir model of the pool for us. They used this 3D survey. They also used our structure map, which is shown here, as well as a cross-section to acknowledge the salt plugging at the top of the reef, the limestone core of the reef, and the dolomite section of the reef to create their reservoir model. Incorporating all the geological data, they came up with this as our 3D depiction of what the reef looks like. You can see the Porter and the Granger wells, the height of the Pinnacle Reef compared to the platform reef around it. Using the known pressure and production information, they fine-tuned this block to be able to have an accurate history match. So we completely match all the prior history and pressure data from the pool. We now had to fine-tune that to match the pressure and production history exactly from all the history we had on the pool. This is the match that they ended up with. You can see the small circles are the pressure points along with the production in red. And you see the match is excellent. We had a really, really good quality match here. So we now have a computer model that exactly represents the pool. With this computer model in place, we simulated drilling either vertical or horizontal wells with a nitrogen flush to be able to purge out the remaining natural gas. I'll show you this picture. This picture, the clear areas in the middle are areas where there's less than 5% of what's already depleted natural gas remaining. The natural gas that is remaining at the point where the nitrogen sweep is completed is in the platform area upon which the Pinnacle is built and in some of the salt plug stuff very close to the top. Based on CMG's modeling, the main reef itself, we recover between 97 and 98% of the gas in place that's there right now, including the whole platform area. We recover between 93 and 95% of the natural gas. So at the point where the purge is done, there's no remaining natural gas in the pool. We now take that pool, simulate that pool with various levels of horizontal injection withdrawal wells to simulate the compressed air energy storage operations. I'll show you this picture here is the simulation case where we assumed that there were 50 injection withdrawal wells. Each one of those little green circles is an IW well drilled across the pool. You can see it matches close to where the porosity is. The porosity scale on there shows the best porosity is toward the base of the reef, but there are better porosity lenses as you come up the reef as well. Based on that 50 well simulation, we simulated 1.5, 2 or 2.5 BCF a day worth of air withdrawal from this pool to feed the turbine. I'll show you this history match here. The red line was assuming 25 wells had been drilled to develop the pool. The blue line assumed the 50 wells, the one that I just showed above, and the green line showed 75 wells. In this particular case was the 1.5 BCF a day air withdrawal rate. Based on the 1.5 BCF a day air withdrawal rate, we're anywhere between about 3 hours with the 25 well case up to about 6 hours worth of the 75 well case that we can maintain the 1.5 BCF a day withdrawal rate feeding to a turbine. That's the kind of input data that the above ground equipment needs to be able to generate the kind of power we're looking at. So as we start drilling these IW wells, new wells in the pool, every piece of geological information will allow us to go back to our CMG model, fine tune that to make sure it's always reflects 100% of the information that we know about the pool. We don't expect it to change very much from what we see now, but it is going to be an evolving case once we get drilling. So next steps, and I'll pull it back to Stephen.
Most of the below ground work is completed in Bayfield CAES project. We're focusing our attention now on the above ground facilities. And this is the compression generation, the utility, gas and electrical connections, and the environmental assessments for the transmission routes to and from. On July 1st, we've been working with the MNRF for a while, and they anticipate proclaiming a regulation on July 1st for the first time ever using CAES and porous rock reservoir in the southwestern Ontario Lockport region. We also have ongoing discussions with service providers to help determine how much electricity the ISO needs for its grid, hours of day that are best suited to stabilize the grid, and the ancillary services that are in high demand, such as black start, spinning reserve, and voltage control. Bedrock is also looking at other elements to incorporate into its meat and potatoes portion of the project, including thermal energy storage, whereby the heat of compression is utilized on the output cycle to boost capacity, green and blue hydrogen at some point, and then also carbon capture and storage. Once the above ground facilities are complete and designed, and the whole package of studies, permits, and approvals is ready to move forward, Bedrock anticipates to conduct its procurements and start the construction process, at which time we will start doing the nitrogen sweeps, as Jim has explained previously. Bedrock is looking forward to positioning itself as a provincial, national, and global leader and innovator in the way that natural resources are utilized in order to meet societal demands and contribute to a more efficient and reliable electricity system.
Compressed air energy storage in Reservoir Rock shows how the oil and gas assets of southwestern Ontario can be used for other things besides production or natural gas storage. It's an exciting endeavor for Bedrock to work on creating the first compressed air in Reservoir Rock CAES project. We're looking forward to many more applications for the oil and gas assets that are present in southwestern Ontario.
I would like to thank you all for attending today and supporting the industry. Jim and myself look forward to attending the Q&A panel and shedding light on any areas we can. Thank you.
Thank you.